Hello, welcome to AISSMS Institute of Information Technology. I, Mr.S.S.Jagtap, Assistant Professor in Department of Instrumentation Engineering. In this video, we will going to see the concept of timer in subject Embedded System Design. The objectives and outcomes. Objectives: list the timers and counters in 8051 controller. Describe the various modes of 8051 timers. Calculations of required delays. After learning this, student will be able to write the code in embedded C to generate the square wave of various delays and to understand the concept of loops and subroutine. Before going to the programming, we will see how the timers registers are loaded. For that, here we take one example. This example is taken from Masjidi book. In this example, indicate which mode and which timers are selected for the following operations. The first instructions: move tmod, #01 hex. In this one, if we see, in a tmod register, the lower 4 bits are assigned for the timer 0. In that lower 4 bit, the first 2 bits are used to represent the mode of particular timer. So here, if we see this 01, these 2 bits specifies the mode, so it is the mode 1 and timer 0. In the second example, move tmod, #20 hex. Here we load the tmod register with value 20. Here the lower 4 bits or lower nibble is a 0, so definitely here we are not using the timer 0. The 2 indicate the timer 1 and mode 2. Similarly, for example C, move tmod, #12 hex. This 2 represent the mode 2 of the timer 0 and 1 represent the mode 1 of the timer 1. While writing the program in a timer, we have to calculate the crystal frequencies and the values that are loaded into the timer or a counter registers. Let us take the second example, example 9.2. This example is also taken from the same book. Find the timer's clock frequency and its period for the various 8051 base system with the crystal frequencies given 11.0592 MHz when counter timer bit of the tmod is 0. We know that here the crystal oscillator frequency is divided by the 12 to get the time period. Here the crystal frequency is given as 11.0592 MHz. So if we divide this frequency by 12, we got 921.6 MHz oscillator frequency. So our time is 1.085 microseconds. If counter or a timer bit is 0, it is used as a timer for time delay generation, and if it is 1, then we use it as a counter. Now program for the timers in mode 1. So these are the algorithms. In mode 1, we use the timer as the 16-bit timer, so that this timer count from the 000 to the FFFF hex. So these values are loaded into the TL and the TH register. In step 2, once we load these timers, then we have to start the timers by using the set B TR0 for timer 0 and set B TR1 for timer 1. After timer is start, now we have to monitor the limit of the time count, maximum limit of the count. When our counter reaches to the maximum limit, in this case suppose it reaches to the 4 time f, then the rollover condition is occurred. In the rollover condition, TF flag is set to the 0, which indicate now our timer is completing the one route from 0 0 to the 4 time f. Once this flag is set, then we have to stop the timer. Now to generate a delay, here first steps we have to load the tmod value register with given condition. Then we have to load the initial values into the TL and TH register, then start the timer. Keep monitoring the timer flag by using JNB TFX instruction. Then once TF goes to high, then we have to stop the timer, and again we have to clear the TF flag for the next round. These are the few examples. In this example, we have to analyze the square wave generated on the pin 1.5. Here, the TL0 and TH0 registers are loaded with initial values 2F, FF. Then we take the complement of the port 1.5, then call the delay and S-jump here, means we are repeating this loop here. Now in the delay is one of the subroutine. In this subroutine we are starting the timer 0. Then this again is a label. In this again label we monitor the TF0 flag. JNB is a jump not bit, means when TF0 bit is a 0, then stay in this line. Once this condition is not satisfied, then it clear the timer 0, means stop the timer 0. Then again it clear the TF0 for the next round. Then after hitting this return instructions, it come from this loop and again is repeating the same program. Now if we have to calculate the frequency generated by this program, now we know that for this each move instructions we require the 2 machine cycles. Move instructions 2 machine cycle. Complement is the logical instruction, so it take the 1 machine cycle. The delay and the jump subroutine is a 2 machine cycle. Set B, it is a bit addressable, so it requires 1 machine cycle. For this count, when we count from the value 2F 3 time F to the 5 time F, we require the 14 counts. So the TF0 flag is set 0 for the 40 count. Then the clear instructions require the 1 machine cycle, and again return instruction is a 2 machine cycles. Now here the total machine cycles are the 28. Here the period is calculated as T is equal to 2 times 28 multiplied with 1.085 microsecond, which is a 60.76 microseconds. If we take the inverse of this T, then we can easily find the frequency. So here the frequency is nearly 16.45 kilohertz. In this calculation, we multiplied this total machine cycle by 2 due to fact that here we are taking only the on time of this square wave. If we calculate the duty cycle, then for the equal size square wave there is a equal on size and off size. So this program is only for the on size or off size. Now let us study this second problem. In this example, we have to find the delay generated by the timer 0. We are not considering the overhead due to the instructions. If we see here, the clear port 2.3 means at port 2.3 we are getting the output. The move t mod comma 01, this is the timer 0 mode 1. So this mode 1 is a 16-bit mode. Then we are loading the TL0 and TH0 values. Then set B port 2.3, set high timer 2, then start TR0, so to start the timer. Again we have to monitor the TF0 flag. Once this condition is get failed, then clear the timer and then stop the timer. Then again we have to stop the timer flag 0. Now to calculate the delay generated here, to these calculations we have to subtract the content in the TL0 and TH0 register from the maximum value, that is this 4 times F minus E38B plus 1. This plus 1 is occurred due to the overflow. Now here this 47C2H is the number which is getting after this hex operation. If we convert this number into the decimal, it is 12370, and when we multiply this number with 1.085 microsecond, then we exactly got the delay created by this program. The program of the timers in mode 2. In the mode 2 is 8-bit timer. It is auto reload mode. Due to this 8-bit timer, it counts the values from 00 to FF. In this auto reload mode, the values which is to be loaded is kept into the TH register. Then the copy of that value is loaded into the TL register. In the algorithms, the same things we have to do while we are doing the programming timer 1. Now let us examine some examples. The programming timers mode 2. This example is also taken from the Majiti book. Assume that the crystal frequency is 11.0592 MHz. Find the frequency of the square wave generation. Now in this program, our initial value that are loaded into the TH1 register is a 5. So to calculate the delay generation, we have to subtract this value loaded in a TH1 by the maximum value. Here the maximum value we are taking 256 minus 0.5, and when we multiply this with 1.085 microseconds, then we got the delay of 272.33 microsecond. Now this is a square wave is generated, so my total delay or a time period t is a double the delay generated, so it is 544.67 microsecond, and if we take inverse of this, then we can find out the frequency of 1.83597 kilohertz. Now in this next example, this example is timer 0 and 16 mode. This program is written in a embedded C language. Again the simple method, we can easily calculate the delay generated. If we see here, the values loaded into the TL0 register and TH0 registers, we have to subtract that values from the maximum values FF. Then we have to add this one due to this overflow effect. Then whatever be the number come, we have to multiply that number with 1.085 microseconds. So here the approximate delay generated is a 56 milliseconds. Similarly, in this example, we have to calculate the delay generated in 8051 controllers through this program. If we see here, this is the 8-bit add to reload mode using timer 0. So this mode 2 is the 8-bit mode, so it can maximally count the value 2 raised to 8, that is 256. So we have to subtract the values loaded into the TH0 register from this maximum value. So this value is 233. Now to calculate the delay, the TH0 value 23 we multiplied with 1.085 microseconds, so it is a 25 microseconds. So in this program, this value is repeated for the 36 times, and to avoid the overheads due to the instructions, here the factor 40 is given. So this program is repeated up to the 40 times. So the total delay produces is 25 microseconds, and this 250 value, and this is the Y value 40. So this total delay generated is a 250 milliseconds. Thank you.